calculus is movement. Movement is simply changing your position, and velocity tells you exactly how fast your position changes. But converting from position to velocity, or vice versa, is much more difficult. This is where calculus comes in. It's essentially the bridge that connects these two. Despite how complicated calculus seems, everyone has actually done calculus before. Imagine you're riding a minecart 1,000 blocks an hour for 2 hours. How far did you travel? Well, getting 2,000 takes calculus. The graph of this situation looks like this. The line here represents the velocity, and let's make a rectangle under it. The width is hours, and the height is blocks per hour. When you multiply the two, you get blocks, or your distance traveled, and this concept is integration. So finding the area under a line or a curve allows you to convert from your velocity to your position. However, it isn't always easy to calculate the area. When you're falling, you're not traveling a steady velocity. You fall faster and faster. This means your velocity graph would look something more like this. Finding the area becomes a little bit more tricky, but let's do what we already know. Let's make the box to estimate it. But now since there's all this area on top, let's make another box. Since there's all this empty area, we can add more and more boxes. Adding more boxes makes a more accurate estimation, and eventually, after making an infinite number of boxes, you'll be able to precisely calculate the area. However, individually calculating the area of an infinite amount of boxes is not possible. So, mathematicians invented a tool to do this easily. Here comes the integral sign. This essentially takes all the boxes and adds them all together. With integrals, you can find the area under any curve, converting from velocity to position, or in this case, blocks fallen. But what's great about calculus is that you can also go the opposite way. Differentiation is converting from distance traveled to velocity. So first, what is velocity? Well, simply, velocity is a rate, how much y increases when x increases. That means when the speed is constant, finding the velocity is really easy. All I have to do is find the slope of the graph, or divide the distance traveled by the amount of time it took to travel that distance. However, when your velocity changes, it becomes much trickier. An arrow shot up has a speed that is changing, so how would you find the speed at a given time? That's where differentiation comes in. So first, let's just take what we know. Velocity is rise over run, so with this graph, let's find out how much the arrow rose from 1 to 2 seconds after being shot. Next, we just shorten the interval of time, and then you can get a more accurate guess of the arrow's speed. As the difference of time approaches 0, for example, like 1.5 to 1.50001, you can get the instantaneous rate of change, or the derivative. So now, we can find the distance traveled given a certain amount of time, and now we know how to find the velocity at a point. But what if I want to know the velocity of all times during the arrow path? Or what if I wanted the graph of my position based off my velocity? Well, first, we need to have an estimated function to model each graph. Let's have the minecart's velocity be modeled by y equals 10, and let's have the arrow's height be modeled by y equals negative x squared. The actual graph would be shifted up and right, but for simplicity's sake, I'll keep it negative x squared. So somehow, we need to make this into another function, so we can plug in any input of x and output a velocity or position. Some people discovered derivative rules, allowing you to convert to and from your velocity and position. The most basic rule is a power rule, where you take the exponent, move it down, and multiply with x, then you subtract the exponent by 1. With the arrow's position graph, you can get a derivative function of negative 2x, which allows you to find the arrow's velocity at any input. With a minecart function, you can do the opposite steps of the power rule, and you'll get an antiderivative function, or an integral function, of y equals 10x, plus the starting distance. So, in summary, an integral calculates the area under a curve by finding the area of a bunch of small rectangles under it, allowing you to convert from your velocity to your position. A derivative does the opposite, finding the rate of change of your function or the tangent line at any point. Using derivative rules, you can make a derivative or an integral function to allow you to input any number to find your velocity or position. This may all seem stupid and useless, but me jumping around takes calculus, as the game has to calculate my movement from my velocity. Also, all the cool contraptions you can see, like that one massive machine that kills the Ender Dragon in one arrow, likely took calculus to build. Even if you don't build something like this though, at least you'll be able to see the foundations of the buildings you live in, the games you play, or even the technology that lets you see this video. So thanks for watching, and subscribe or you'll be